Mohammed, now so better everything. You say they can't show me something. Ah. We better not lose. The passport is different.
China to go. They go live, so if you enable as people they go up and down when you go live. The sounds of
Yeah, I never do this.
You know, it's here. No, understand. Okay, you know what? Okay, thanks. Well, now then we have to transplant to
Yeah. 928 5277 2838. Yes. Passport 949020. Yeah.
You have to share that, but I don't want to do it now. I want to do it. I,
Good morning. Yes, okay. So I'm back. I'm so very happy that I got a little bit more time. Okay. So what I want to do is I want to show you a little bit more measurement, but not so as complicated as yesterday. Because remember now we go back to the stage where things are more abstract. So we go out of the forest and then we can see not only single trees, but the forest. No, that is sometimes good technique. And that is what I just want to say. show you a little bit what you can do with these measurements. And I also brought some small experiment with me so that we can check if we calculate the right thing. Right? Let's see. And then in the second part, I'm going to talk finally about communication, frontal communication, and that will be done with slides. But we will also calculate a little bit in between, don't worry. Okay, so so the first thing I want to do with you is look at the sequence of measurements. Right? What happens if I make two measurements after each other? Right? And so imagine we have the following situation. So let's first write a sequence of measurements. And the sequence of what kind of measurement? Of projection measurements. I will tell you in a moment again what I mean by that. I think this was number 6. And the situation is like this. Let's take the simplest situation that we can think of, right? Namely, that we have a qubit, okay? And we make measurements. For example, we can have this polarization qubit. You remember there was 2 states. Do you remember which ones? Polarization in this direction was called vertical polarization, and horizontal polarization. Of course, you can also take a different basis, diagonal and anti-diagonal, or circular polarized, right circular polarized, or left circular. But let me say I prepare some state psi, and then I make a measurement. On the transversal plane, I only let through, sorry, maybe I should put this through the middle. I only let through the light that is polarized in this direction, where this is the angle θ1. Right? And then afterwards, I have a second filter, and I only let through the light that is now, let's say, polarized with respect to this angle here. This angle can be different than the first angle, so I call it θ2. And then I have a detector, and I measure whether the photon arrives here or not. So a single photon, it has a certain state, a certain polarization state. Let's assume that this polarization state is just 0, which means in our case this is vertical, right? And now we want to know when the photon goes through these 2 filters, what is the probability to detect it? So how is this related to measurement? Can you imagine what is here the measurement? I mean, measurement usually has always 2 results for a qubit, right? So how can we relate this filter system where something goes through or not through to a measurement? What do you think? Can I interpret a filter as a measurement? Are there 2 possibilities? Let's say, yes. Yes. And what are the 2 possibilities? If I just look at one filter, Okay, it goes through or it stops. Okay, there's two possibilities. That's absolutely right. And if you go through, then this means you project onto this polarization direction. But if you don't go through, on which direction do you project? Why this and why not this or some other direction? Well, this is like I look, do you have a component in this direction? If that is the case, then you get through. If you, I mean, let's say with a certain probability, you get through, you will calculate it. The opposite event is that you are projecting onto the orthogonal, right? So basically, each filter decomposes the state space into two or the identity decomposes this into two directions: the direction in which it points and the orthogonal direction, right? So, for example, if I want to write down um, the projector that corresponds to the first one, so psi goes first to the first one, okay, and then I can write down the projector like this, where the projector is given by cosine theta times 0 plus sine theta times 1. This is not really a projector, right? This is just a state, right? This is the state on which I project, but the projector means I have to repeat this here now. So how do I write this? I don't want to use this thing here. So I write below here cosine theta 0 plus sine theta 1. And you see, I use here, so you must think of this coming behind this, okay, so that we have something of the form theta, and this should be theta 1 because it was the first one, theta 1. Theta 1, where this thing here is theta 1. Okay, this is a projector. Do we know this already? Is this kind of clear? Okay, then I have a task for you. And can you calculate what this state here is? So this is the state, let me call it state psi 1. This is the state after the first one. So here we have state psi 1. Okay, can you please just calculate this? So with your neighbor together, try to calculate what comes out here. Okay, you know what psi is, it's just 0. Okay, so you have to take this operator and let it act onto 0. Try, first of all, guess what comes out of it. What will come out of it? Which vector will come out of it? In which direction will the vector point? What do you think? It will point into the direction of theta 1. Right? That's at least what you hope. Okay, so give yourself 5 minutes and try to calculate this together with your neighbor, and I go through and help you. It's too hard. Okay, 5 minutes. Thank you. Or if you are much faster, then let me know if you've done this. Yes. Hey, I just want to say, I'm very sorry that I put this in the second line, because then it looks like it's separate. This was actually supposed to be behind, here, you know? Here, this thing here comes behind here. So we have a cat multiplied with a bra, and the bra, this thing, will act, this is basically this thing, will act onto the zero. And then you have to ask yourself, what happens if this thing here acts onto a zero? Then you see here is cosine theta zero acting on zero. Zero on zero is one. If one, this one here acts on zero, then one on zero is zero. And then you get something that is probably proportional to this vector, but it has a factor that comes from here. Okay, sorry. What's that here? So, do you have any results? Anyone a result? Yes, result for them? Cos theta 1 times? That's all. Oh, so you just get a number. But I was asking for a state. You know, this is a state, right? So now this must be some vector. Oh, and number is not enough. Yes, okay. I understand you like this. Cos theta 1 times theta 1. Yeah, theta 1 is just this thing. Yes. Okay. Let me do it in front. Then I hope we can everybody agree on it, right? So I'll do it here in front of you, and then it should be easier. All right. Is there anyone else who got it? Did you get it? We're still not finished. Okay, don't give up. This is just in the beginning. You have to get used to the formulas. No. Okay, I'm going to show it to you. So let me do it here on this half. Yeah. Say again. Theta 1, cos theta 1, cat theta 1. Perfect. Thank you very much. That's the result. Cos theta 1, p theta 1 onto 0 is cos theta 1 times theta 1. Let me check this, okay? So this is the claim. And now let's calculate it together, okay? So, okay, what do we have to do? Well, we have to calculate P of theta 1 times psi. Yes? And P of theta 1, now I get C6. P of theta 1, psi is just 0. Everybody happy with that line? Okay. Now, I write here P theta 1. Well, P theta 1 is theta 1 times cosine theta 1 times 0 plus sine theta 1 times 1. But 0 and 1 here are brass, and here comes a 0. Can you still read this, or is it too small? Can you read this? Okay, and do you agree with that? Look at this. This is basically theta 1. This thing here, right? So I just wrote this P theta 1 and theta 1, bra theta 1 times, cat theta 1 times bra theta 1. Is that still okay? I basically just copied from here, right? Instead of writing the long formula, I just wrote the short formula, but I expanded the second part here, this bra theta 1. I expanded it because now I want to make it act onto the 0. And for that, I need to know how to express it in the basis of 0 and 1. Because remember, everything is super simple as soon as you just have basis vectors. So as soon as you have a representation of all vectors in terms of the same basis, because then you can use this orthonormality of inner product of the basis. So are you happy with this? Is this kind of is this clear that this comes from there? Who is not happy? And I don't trust you. Okay. Yes. Why only one? Yes. Okay, wonderful question. Why only one? Yeah. Okay. So in general, you know, if I have any cat psi and some bra phi, let's say it would be like this. Let me call this not psi because we have already psi. Let me call this lambda. Okay, so where this is a cat and this is a bra. Okay, this is an operator. Why is this an operator? Because I can map now. I can let it act onto some onto some state psi, and then I can calculate what comes out of this, and I can tell you what comes out of this, namely a vector. So I can map this vector psi onto another vector, and this means I have an operand, linear operand. Okay, I do it in a linear way. So how do I calculate this? And now please look at the beauty of this formalism. Really, instead of writing down a big matrix where I have now many entries in that matrix, depending on the basis, I just write down this very small, short expression, and then I tell you the rule how to calculate. All right? So the rule is this: if you write this thing, then you take the lambda from here. I'm just repeating. Then I repeat the phi. This is the bra phi. Sorry. And now I put the psi directly behind it. But do you see what I did? I left out one of these lines. And now I have inner product. This is the notation for inner product. So this is a number. This is the vector. The number times the vector, or vector times the number doesn't play a role. You can swap the number of the vector. Then you get something that is, if I call this thing here, let me call this alpha. Then the number alpha, you know, is the number out of C, of the complex numbers. Then I get alpha times lambda. I just took this number and put it in front. So now I know the vector psi was actually mapped to the vector, to a multiple of the vector lambda. Right? And if I want to calculate this alpha, then I have to write this thing here, both of these vectors, phi and psi, in the same basis representation. And then it becomes super easy to calculate. Let me show you. Okay, so I want to show you this at this example. So you see what I had here. So let me make this example. So now I have a vector of, it was called theta 1. Yes, theta 1. This is a special vector. Now I have an operator, which is a special operator. It has in both the bra and in the cat the same symbol. Okay, this basically means a projector onto this vector theta 1, because here it has the same as there, and projectors have this property that they are idempotent. You know that we learned yesterday from the day before, no, yesterday from Andreas. Maybe it was the day before yesterday. From Andreas, day before yesterday. Yesterday. We heard idempotent, and what he basically said, so if you have p theta 1 and you square it, then you get back p theta 1. Let's do this together, okay? So this is called idempotent. I don't know how to say it. Idempotent. It just means if you take the power of it, you get back the original one. No? So how can we calculate this? This is theta 1, and then acting on theta 1, right? Oh, can you see this? No, you can't see this. This is nonsense. Sorry, I write it on top there again. Sorry for this. Let's put it here. So theta 1. So I want to calculate p theta 1 squared. And I say this is theta 1 times theta 1. And then I have to put theta 1 times theta 1 behind. Right? And now the trick is that I put these two things together. So instead of putting the brackets around like this, I can also bracket here and there. This is also possible. So I get theta 1. Sorry, this was the wrong way around. Again, theta 1. Okay, then I have here theta 1. Okay, and then I have in principle a theta 1 acting on this thing, so acting on theta 1. Okay, and then here another theta 1. So basically, I have now made a different choice of bracketing. So I want to take this one onto this, and they talk to each other because this is a bra, and this is a cat. And if I write them together, then I have to repeat the first one, theta 1, and then comes the theta 1. And now I use one of these lines, this line I use, then I have theta 1 like this. And does anyone know what that is? This onto this gives what? 1. That's right. So I get for something stupid, I forgot something. Here was another thing. Okay, so I must not forget this. Theta 1. So I get for this thing here, I get 1. So now I just copy everything, theta 1, and this is it. But this is nothing else than p theta 1. So p theta 1 squared is equal to p theta 1. Right? So this is how you can calculate with these things. And imagine I had written down a matrix. I would have had a 2 × 2 matrix, 2 times 2 × 2 matrix. I have to do many multiplications to get this out. While in this formalism, I get it. So now let's use this to calculate this one. All right? So this was just a side calculation. So now I take pi theta 1 again 1 to 0, and I already had it. I had this thing. Let's just copy this again. So I have theta 1, and then cosine theta 1 0 plus sine theta 1 1 to 0. Everybody happy so far? Is this still okay? Yes? Okay, now let's calculate this together. So now I want to multiply, this is linear, you know, so I can now take this thing and multiply it with this plus this sum multiplied with this. All right, so can you still see this? I'm going to write this as theta 1, I just repeat. And now comes cosine theta 1, 0, 1 to 0. See what happens. I'm using one of these lines. Cosine theta 1. I hope you can do this. Times 0, 0 plus. And now this one, sine theta 1. And then I have here 1 to 0. Do you get this? What I did there? Yes. Everybody happy with that? Yes. Okay. Because now we can calculate actually what comes out, and we can check whether the claim was correct that was made over there. So how do you do that? So do you know what this is? 0, 0? What is it? 1. And 1, 0? 0. Okay, so then I get is cosine theta 1 times theta 1. Because this was 1, this I forget, and this cosine theta I can just write in front of the bracket. You know, a number, where the number is, doesn't matter in this form. Okay, so now we calculated this, and this was correct. All right. So now what did we get out? I come to you in a second. What did we get out? Well, we got out that after the operation, this is proportional to a vector that points in this direction. So the light wave comes in, it has 2 polarization directions, then 0 and 1, okay? And it is now projected onto this direction. If it comes through, this is what happens. Okay, so if the thing goes through, then this is what happens. This is now a filter, okay? And what we actually want to calculate is what happens after the second filter. But there was a question. Who had it? Not a question. It's common. So this idea, of course, is nothing else than. All right, so we have that, and now we can calculate what happens here after this. Sorry that it takes so long, but you know, better we do this correctly, and then you know how to do it in the future. So, okay, I lost my notes here. Everybody happy with this? Okay. Oh, you're not there. Okay, so now. Yeah, now I want to calculate the second one. So the state after that thing, yeah. And I want to remark one thing. Look at this vector. That's not a normalized vector, right? So this our states are usually normalized. So we still have to divide by the square root of the probability that this happens. And the probability that this happens is actually given by the cosine squared of theta 1. I'll show you. So can I get rid of it? Yes. Thank you. Thank you. I will just erase this one. Okay, so first of all, I want to calculate. Maybe I leave it away. The probability. I don't do it. I calculate now what happens after this. So this is psi 1, and here's psi 2. And then I normalize directly. So let me first calculate what goes through. So psi now goes to first p theta 1 psi 1. This we have already calculated. Okay. This is for theta 1, and then it goes to theta 2, and then I have to do this again. I have to take this one and put p theta 2, the projector, onto the state theta 2 there, sorry, which is p of theta 1, and then psi 1. So this was not psi 1. Okay, I could have written it differently. Let me write it one more time. Sorry. This thing here is psi theta 1, or psi 1. Psi 1. And then this is p of theta 2, p of theta 1, psi 1. Okay, so now we have to calculate with this thing. And in fact, question. Sorry. Correct. Correct, right? That's what we want to ask. The P2, P theta 2 has psi 1. This is my my Roman 1. So at this point, after this filter, we have psi 1. And in order to calculate psi 2, this here is psi 2. You know, we have to, so this is psi 2, this thing. We have to take this one into account. Okay, right. So now the trick is that we actually have to normalize this whole thing, right? We have to normalize it, and I'm going to just normalize the last one. So I will say the operator, the cross operator, or the measurement operator that I have here, describes how this whole thing goes, namely P theta 1 times P theta 2. And then if I really want to do the thing correctly, I have to normalize this. Okay, so I normalize this by taking the square root of the probability, to get theta 1, theta 2 and theta 1. The sounds now a little bit complicated, but this probability is given by the following. It's given by taking this thing in the inner product with itself. Okay, so taking the operator P theta 1, P theta 2 with P theta 2, P theta 1. So what is happening here? And then, yeah, this is the probability. So what is happening here? Look, I have this this operator acting on psi, and it gives me some vector. Okay, but I want to normalize this vector, and the normalization of that vector is given by dividing by the norm of this vector, right? But how do I get the norm of this vector? I take the inner product of the vector with itself. That gives the norm of the vector squared. And then I take the square root. That's why I have the square root in. All right. So I could have written this thing as P theta 1, P theta 2, psi, and then this expression here and the square root of this. But before I write that here, I want to calculate this. Can someone help me to simplify this? So this P theta 2 times P theta 2, what is that? That's what? That's 1? It's 1? I'm not sure. I mean, if you take the square of a projection operator, then it's the same. You get a projection operator back. So remember what we proved before. We said that P theta times P theta is equal to P theta. This is what we showed, right? So in other words, I can write this thing here as P theta 1, P theta 2. These two things, the product gives just 1. Okay. So what I get now is just psi P theta 1, P theta 2, P theta 1. So, okay, and this is what I can put into this formula here now. I can write this as psi P theta 1, P theta 2, P theta. All right. So this is what we have. And now I want to convince you that that if I take 0 in, and now I calculate the state, okay, let me call this the state psi theta 2, but it's a normalized state, so I make a little head about it. So this thing, psi theta 2, psi 2, Rho 2 with a head, and it's normalized, will just be good question. What will it be? Any guesses? Any guesses? I mean, what has to come out here in the end? So first you project onto this, and then you project onto that onto the second one. So what will come out here is theta 2, which is cosine theta 2, 0 plus sine theta 1. Okay, so this is an exercise. Okay, this is exercise to show this. But this is what must come out, and that is maybe not so surprising. But what is the probability to measure theta 2 and theta 1? Well, it turns out that it is cosine squared. So it's first cosine theta 1. This is clear, cosine squared theta 1, because you have to first go through this. So it's the probability that you go through this times the probability that if you went through this, you will also go through this. And that's given by cosine theta 2 minus theta 1 squared. And even though I can think about it and find this out, I can also calculate it just by calculating this thing. So this is also exercise. Look at this thing and calculate. Not now, but do it for yourself. It's a good exercise. And then I want to motivate that this is really must really be the result, because you know this one is clear that this is the probability to go through here. Okay, because you know that you go through here, you have to have this angle theta 1, right? In there. So you basically, we can also write it like this: the probability of just theta 1, you know, if the initial state is 0, is given by the expectation value of p theta 1, 0. And this thing is just cosine theta 1 squared. Sorry, yeah, because you know, if you calculate this thing, then from the one side you get a cosine theta 1, and from the other side you get a cosine theta 1, then you get a cosine theta 1 squared. Okay, so can you understand this, or am I too fast? Maybe too fast? Yes. Too fast. Okay. Good. And then we do this in handwork. So this is the theta 1, this thing here. I'm now just calculating the probability to go through the first filter. This thing is given by this, right? I just took the p theta 1 and put it in. Everybody happy? Yeah. Okay, so now this thing is nothing else than theta 1 squared. Yes? Yes. Okay, so now let's calculate what 0 theta 1 is. It's always the same kind of calculation. Cosine theta 1, 0 plus sine theta 1, 1. And this is equal to the 0 x onto the 0, right? We get the cosine theta 1 in front, cosine theta 1, 0, 0, plus sine theta 1, 0 times 1. And this thing here is 0. And this thing here is 1. Okay, so I'm left with cosine theta 1, right? And if I square it, what happens? I just get this way. All right? So this thing here is here, right? So what happens if you are through here and then you want to go through here, then basically you are already in this direction. Okay, you are already in this direction, and you have to still get to here. And the angle between here and there is actually this angle here is theta 2 minus theta 1. All right, and I get the same result now going from the theta 1 to the theta 2 as here, but just with the cosine theta 2 minus theta 1. Okay, so you can believe it, but you can also check it by direct calculation, right? And now I want to show you the experiment. So I need some help from the man on the camera. Let me just get him. Okay, so we are going to try to do this here with polarization spoilers. Yes. Okay, so we are going to try this. And then sorry. So I'm in front of the camera. And I have these polarization filters. These are kind of polarization filters. Can you see? Yeah, okay. So this is fine. So if I turn this thing around, nothing happens, right? Because this is just, the light that comes through the polarization filter comes from where? It comes from there. From this side, light goes through here. Okay. Actually, not sure. So I'm standing in front of the camera, right? So the light goes through here, right? Because the camera is on that side. So it's like the detector is on that side. But this is a polarization. Like this theta 1 thing, and I can turn it around like I want, but nothing happens. Why is that? We don't see any change in the intensity. No, it looks always like half dark, isn't it? Yeah. So why is that? Can anyone explain it? Yeah, you can hold it. Why is that? What is the light that comes from these lines? What polarization does it have? Yeah. It's not polarized. And what do we mean by that? It doesn't have an electric field that is going like this or like this. I mean, is an electromagnetic wave not always having a certain polarization? Yeah, that's true. But the atoms that are in the lamp, they emit light, and that is light of different polarization. So some of it is like this, some of it is like this, some of it is like this. In fact, it's in all directions. That's called naturally polarized light. Okay. And some people call it unpolarized. It's true. And then what happens is if I come to the filter over there, half of it is lost because half of it is in the wrong direction. You know, there's two directions, but half of it is not, and that's why the thing is halfway dark. Now I want to see whether I can make it less dark. And I'm going to use the cell phone. Let me show you the trick. Can I have the cell phone? So that my task is not. My task is now, I want to have it not gray, I want to have it totally transparent. Okay. Whether I can do it, I don't know. I've never done it. So it's my problem. So where are we? Okay, I need, yeah, no, I need someone to stand here with the cell phone. Then the cell phone can come out. Okay, so now I put the thing in front, and what I see cut, so not but what I want to see actually, in fact, I wrote it. Look at this. Wow. Huh? Now it's transparent, right? Before it was straight, so no one ever did. So so this is like so much in the real stuff. Instead of for the water, right? So much more colorful. So this is the darkest side. And what is the darkest? This is the most picture light, right? Now I turn it off, and this is it. Yeah. This is the most dark, this is the darkest, okay? So what do we conclude? In which direction does the light come out from the cell? I mean, the cell phone is the source, the light source, right? And if I turn it like this, then I get most of the light through. So what does that mean for the polarization of the light from the cell phone? First question, is it polarized, the light that comes from the cell phone? Or is it not polarized like naturally? What do you think? Who is not polarized? Who doesn't care? So this is funny. I also think, you know, because we see a difference in the intensity, it must be polarized. And in fact, we can find out which direction it has by rotating it so that we get the highest intensity. And it was like this. Let's check. Sorry, that's not even. Okay, so I think this is like this. Okay, so this here is the polarization direction of the screen. And the screen was like this. So I think the polarization is horizontal. This thing gives on horizontal polarization. Why? That's maybe a different question. But we can really think about it because this is a LED screen or is it LCD? What do you know for itself? LED. Okay, it's LED screen. Okay, so why is the light that comes from LED screen polarized? That's one question. Another question is, I want to now use this thing to do my experiment. Okay, so my zero direction is actually vertical, but here the thing here is polarized in horizontal. What comes from the, but I'm going to call this now zero, just because I did my calculation for zero. Otherwise, I have sine and suppose it's not much to it. But let's say this is now my zero direction. And now I take two things behind it. So now I need So I have here a second. Yes. And when I turned the thing around, he saw that's different. He saw different colors. Right, three colors. He saw three colors. Okay, so that could mean what? I mean, if I see the red color and not the blue color, that means that the blue color maybe has a polarization that is orthogonal to the red one. I mean, orthogonal to the direction of the. Might be so, but I want to leave that behind. You know, it's an interesting question because I want to go to my extent. We come from one point to the next, and then we have to extend the whole thing, and then no one else. So we don't want that. Leave some words for later or for others. So I have now these two things, right? And look about maybe the first is like this, not problem. So without form, if I turn this around, you don't see any change, right? So now I have two things behind it. Okay, and now I turn one of them around. So, then they start. This is what we have. This is the situation that one foil is pointing in this direction, and the other one is from. And I don't get this. Right? But I want to go to this. So we know that these things have different directions. I do them like this, and it's just gray like one. So then they compensate. This is basically the proof that P squared is P, right? If you do twice the same thing, it's as if you do just one. Look at this. This is not the. This means P squared, right? So you see our calculations like quite useful because we can do this. Right. So now I'm going to use this with the telephone because the telephone is basically giving me the psi. Remember how psi is this. Okay. All right. So I have the one thing. This is my foil, my first foil. I'm going to just change it a little bit in this direction. Okay. Forget about the color, just look at the next. Okay. So now I take the second one, I take the parallel. The first one that means P squared is equal to B, no problem. But now I'm going to shift it a little bit, and then you see it comes back at some point. And it is basically a very clear saying. But you can change also the first one around, so we can make the first one here. No, and grab here, and if I take the second one, the same thing. This is P squared, right? So I turn it now around, then I should see one point where it is like this. So in this situation, what is theta 2 minus theta 1? What is if I get no lights? What theta 2 minus theta 1 equal to 0? Cosine of theta 2 minus theta 1 equal to 0 is what of theta 2 minus theta 1? Must be. No, if theta 1 and is equal to theta 2, then I get cosine of 0. Then I get a full thing. Then I get everything goes through, right? But if it is dark here, that means theta 2 minus theta 1 is equal to what? So what does it mean? 90 degrees. So they are from theta 2, the filter theta 2. So the situation is this. That thing here is like this, it's orthogonal to this. Then nothing goes through. Okay? So theta 2 minus theta 1 equal to 90 degrees means that the second angle here, that this angle here is 90 degrees. Okay, then nothing goes through. This is exactly what I see. And we could now kind of measure everything, all the angles, and see whether our formula is correct. The formula would be this thing here, where I have this formula. If we really do the angles correctly, then this formula should come out, but not as probability, but as intensity. So the intensity should be this factor times the initial intensity. And at some point, it gets dark, and if this is 90, if theta 2 minus theta 1 is 90 degrees, or if theta 1 is 90 degrees, it's also dark, okay? We can check that all, okay? And it's kind of fun experiment. And we have to explain the colors. And I want to just show you that I put a thing here in between. This is just a normal, what do you call this? Tape. Not tape, so to say. Cellular, right? So I put that in between. So I don't. So what I actually changed it to rotate this. So just buy yourself this stuff can be bought by from Amazon. And then okay, for next it's called polarization coil. Polarization. And you just buy it. I bought a big one and cut it. Right? And it's especially good if you do outreach, because the people, the learners also. All right, so this is this, and I would say we have to make a break. So as I told over, what time is it? 9:51. Yeah, let's make a 10 minutes break and then start. Well, what do you think? Or you're still fit? You can also go on. Break. So, can I? Okay, I want to continue. And the plan is now, I'm just showing you that this is what kind of animal this is. You know, the operator that allows me to calculate the state after the second foil or the second filter is this operator here, right? What we have here in the denominator is just a normalization constant. So this operator here is not a projector, right? So if in general, if you look at consecutive measurements, then you can also write down a measurement operator. This is called a measurement operator, but it will not be a projector. And to calculate the probabilities, you know, last time we had these effects, you know, we had effects that were, or how do you say that actually? It's not effects. Effect. Sorry, yeah, effect. It's an effect. Okay, so we had effects and we had measurement operators. Okay, so let me shortly write this down again so that we can identify them. And then we know where we are with the formalism, because it's extremely helpful to just know this formalism, because then suddenly you can make general statements about, for example, classical teleportation, why it doesn't work, because there is no such measurement that could do it. You know, if you want to make a general statement, you have to talk about all possible measurements. And for that, you need to have a strong expression that is general enough, you know, and then you can calculate things. So first of all, the last time, last session, we had measurement operators, or sometimes called cross operators. Cross operators. And let me write this correctly. Cross operators. And we had effects, sorry. And the cross operators we wrote with the M. So there was always a family of cross operators, so several cross operators for each outcome one. And the effects we had with EI. And the relation between the effects and the cross operators was that the adjoint of the cross operator times itself gives the effect. So this is what we had last time. And now let's identify here the effect. So first of all, the measurement operators work like this. So state after the measurement. You need the measurement operators to calculate that. So you go with psi, initial state goes to mi psi. And then you have to normalize it. And the normalization is given by psi mi dagger mi psi. So this is basically the effect. Okay. So this is mi psi square root psi expectation value of the effect psi, and this thing here is nothing else than a probability to get this result pi. So the probability is given in terms of the effects, and it has expectation value of the effect, right? And then we had a rule, namely that the sum over all the effects must be the identity. If this is the case, then you describe a measurement where all the effects are given in this form, okay, which means they are positive operators. So that means their expectation value is always positive. All right, so now if this is the case, then what is it here? So here I have the what is the measurement operator? Can someone tell me? Let me put here a theta 1, theta 2, because this is the two parameters that play a role. So the measurement operator, where can I see it? I can see it where I see the state shift. So it must be here. So can someone tell me what the measurement operator is? P theta 2 times P theta 1, okay? P theta 2 times P theta 1. Okay, and what is the effect? It's now we have to adjoin this thing, P theta 2 times P theta 1 adjoined, and then P theta 2 times P theta 1. Actually, I don't have to do this calculation because I have already calculated it here. You see here, I got this thing. You see, I wrote actually the P theta 2, P theta 1, I wrote it here in the opposite order, P theta 1, P theta 2, and that is exactly what happens here. Because if I take a joint of the product operators, I have to change the order and join them singly. But these operators are self-adjoined because each of them is a projector, and then I get out this P theta 2, P theta 1, P theta P theta 1, P theta 2, P theta 1. And now we can ask, is this a projector? And the projector would mean that this whole thing, if I square it, then I get this, but this is not. Okay, so this is not a projector, and since it's not a projector, we are not dealing with a projection measurement. Even though we have two single projection measurements, the composite, the consecutive projection measurement is not a projection. That's very important. That means we are dealing with something that's more general, and it can be written in terms of these things instead of using projectors, where if I use projectors, then this thing here is basically, if MI is a projector, then MI dagger is MI, and MI dagger MI is MI dagger squared, then it would be MI. Then this would also be a projector, but this is not true. So in general, we deal with something that's not projected. And the only property they have is that this thing is true and that PI is equal to MI dagger MI, which means that the expectation value of this thing is always positive. And we say it's a positive. So this thing that has such a, we said it again, if I have such a family of positive operators, then this is called a positive operator valued measure. Or in short, it's called a QVM. And both measurements are described by QVMs and not by projection value measures, which would be P. So this is the general problem question. If you know that, then you know that. All right. So with this, I want to come to the end of the measurement section, and I come to the communication section. Now I still have maybe 20 minutes. Then I show you the most important things. Yeah, 20 minutes. All right. Are there any questions concerning this measurement section? There was a lot of things that I wrote in between. I'm sorry for that. Okay, but you can read this in the book of Nielsen and Schramm, it's called Quantum Computing. Now maybe I should write it over there. Otherwise you won't see it. Okay, I write here the book Nielsen and Schramm. Those are the authors. And it's called Quantum Computing and Quantum Information. Okay, so this is 2011 was the last edition that I have. So I think Oxford Press or something. But you'll find it. This is one of the famous books, and you find it for free on the internet. Okay, so if you read there about measurement, they describe everything in PDFs. All right, let me come to something new, except there is an urgent question. You don't want to leave without showing the calculation. And how it's done in practice. Okay, so then I'll do this. Let me go to share this here. And then I want to go to the beginning and do this. Let's just take a photo of this. Right. Okay, quantum communication and measurement. We know this slide already. And continue to share. And yeah, we had this already. I just want to show you the thing that we do today. So today we will ask the question, what is quantum teleportation? Teleportation with linear optics. And then maybe we even get teleportation of images with nonlinear optics. And teleportation of any state of light. That's really a challenge, but we can do it. So here is a photo of my collaborator, Andrew Porras from WITS. He's an experimentalist, I'm a theorist, okay? And he came from optics, and I came from quantum mechanics. In fact, in the year 2008, he showed me this article, Twisted Photons, by Kuo and Torres and others. And later we worked with Kuo and Torres. And this is about light that has orbital angular momentum. You think that's impossible? Because we know light is polarization, it's like spin. But it has also orbital angular momentum. What can we think of this? Right? It's very interesting. And it gives us the possibility to use something that's not only two levels, but more than two levels. In polarization, I just have two levels, namely horizontal and vertical. But in this, we have more. So Andrew came from optics, and I came from quantum mechanics. And we after some time, really talked to each other because we spoke the same language, right? And then he did more quantum optics, and I did more optics. It's very fun. So here's a plane wavefront. So that's 50 laser light. You know, if you shine a laser in this direction, then on a transversal plane, it's more or less flat. Okay. But you can also make a screw-like form of the wave, you know, and then it's like it has a certain rotation sense, and it transports orbital angular momentum. What does that mean? That means if you actually have a charge there, the charge will start to rotate. Okay, like in this sense, or the other way around. And that means the wave carries orbital angular momentum. If you ask for the value of orbital angular momentum, it's always a multiple of h bar. H bar carries the units of orbital of angular momentum, namely joules times second, okay, or electron volts times second, depends on with what you are dealing. And how do I produce such a wavefront? Yeah, it's very easy. You just take a little phase plate that has a different thickness depending on the azimuthal angle that goes wrong. Okay, so in the middle, the beginning it might be very small and then very thin, and then it gets thicker and thicker. Okay, and if you like this, okay, so I have phase shifts. This dark means 0 phase shift, white means 2 pi phase shift. Okay, and you go once around. Here in the middle is the singularity. There's a point that's not really defined. So that's here in the middle, there is not really the electric field is 0. Okay, and what you then see is that you. Oh wait a minute, this would be nice. Maybe I can put this in, then I can walk around. Give me just 1 second. So what you see in the middle is you see now these light modes. They have different numbers of rotation. So for the one, here's 0, this one. Okay, so this is the intensity of a so-called Gaussian beam. And then here is orbital angular momentum -1. That means you rotate from 2 pi to 0. And here's +1 is from 0 to 2 pi. And then you can have also 2 times this. So you go from 0 to 2 pi until here. And then from 2 pi to 4 pi here, right? And then you rotate within one wavelength, you rotate twice around, not two screws. And you can have 3 and so forth, but you see the hole in the middle gets bigger and bigger. All right, so if that is the case, then we can actually do quantum communication with this light. How do we do this? Well, we take these wavefronts, and here's the intensity pattern. We saw that already. And then we just signal. So I have now an alphabet of a total of 7 letters, okay, that I can send you, and you can measure this. But how do you measure it? How do you prepare it? How do you measure it? Okay, the way to do this is actually using spatial light modulators. That's little displays that are LCD, liquid crystal displays, okay? And they have 1 million pixels on a small, say, 2 centimeter squared surface. And you can program them such that you give a phase shift here that's 0, here that's 0, here that's 0. And then if you go 3 times around, what orbital angular momentum number is character you get by that? How many times does it change per wavelength? Yes? Goes from 0 to pi, how many times? Look at the pattern that's shown there. How many times do you see black? 3 times. And how many times do you see white? 3 times. So you go 3 times from black to white. It means you make 3 rotations per wavelength. And that is OAM value, orbital angular momentum value 3. Okay. And now how can I do this? Well, I take a laser, I shine it on this SLM, and then in a reflection, I get out this light pattern. Okay. And this light pattern is just the intensity, but in fact it has this screw-like wavefront that goes around 3 times per wavelength. Okay. So that's that. And then you can program all these different wavefronts. You know, so this is OAM L0, L value 1, 2, 3, 4, and higher one. You know, and with that we can signal. We send signal from here to Accra. I don't know, it's maybe too much. So we need probably 3 stations in between where we refresh the signal, but we can signal. And now we can compare to polarization. You know, the polarization can be written on the Bloch sphere. Can anyone explain the Bloch sphere to me? You know how the Bloch sphere works? So maybe you can see it from the sketch here. Try to tell me what you see on the North Pole of the Bloch sphere. What polarization do you see there? Yes. What's on the North Pole? That's L. What does that mean? Maybe not clear. It's left circular polarized light. Okay. What do you see on the South Pole? Right circular polarized light. Okay. So what do you see on the x-axis? In the east, in the west, it's horizontal. In the east, it's vertical. Okay. So basically, we know that you get all states by superposing the basis states. It depends what basis you want to use. We use always horizontal and vertical, and we knew we could that by polarizing by just taking 50-50 superposition of horizontal and vertical. I make it here. I get this here. Okay, which was the diagonal. If I start here, yes, then I get anti-diagonal polarized light, and they are on the. This is actually the y-axis. They are on the x-axis. Okay, so superpositions of H and B you find in the equatorial plane, and superpositions with a pi half phase shift, which gives you circular polarized light, you find in the z direction. Okay, and in this way I can map all states, all superpositions of 2 basis states on the sphere in the 3-dimensional thing. Why don't I need 4 dimensions? Because there is a normalization conditions that reduce me to 3 dimensions. Okay, so now I can do the same thing using alphabet of OAM states. So here I have OAM equal to 2, OAM equal to -2, and on this side I have then the superposition of 2 and -2, and here the negative superposition, and that gives me diagonal, anti-diagonal. I mean, it's a little bit like this. Okay, so we can play the qubit game, but we can also play a QDIT game. That means D levels, and we have entangled photons. So that's also interesting. So in this case, I shine a laser into a nonlinear crystal, and then I get spontaneous parametric down conversion. That means 1 photon in blue becomes 2 photons in red, and they have different polarization. Then we orthogonal polarization. And in a certain type of down conversion, maybe type 2 phase metric. And here I have also in the spatial modes, I have counter-propagating or not counter-propagating, but counter-rotating OAM modes. And in fact, I have not only L1 and L-1, I also have L equal to 2 and L equal to -2. And even L equal to 3 and L equal to -3. So what comes out here is a superposition of all different values of L, where 1 is the opposite of the other. So 2 and -2, 1 and -1, 3 and -3, 4 and -4. And this superposition is an entangled state. And it means that I can actually make measurements on this side. If I measure on this side +1, I must find here -1, and the other way around, right? And this is a typical feature of entanglement, and we can use it to do this quantum key distribution. This is how it looks like in the experiment. You know, I mean, not really, but this is an abstract way of writing down a scheme, experimental scheme with lenses. All right. So this is this. And then we have these correlations of OEM values that I told you. So it's basically, you know, if you have L equal to -2 here, then you have L equal to 2 here. Okay? And if you have L equal to 6 here, it's a little bit faint, it's L equal to -6. So it's only on this diagonal of these correlation matrices. All right, so we can use that to actually do communication to a satellite and back, okay? And quantum communication is if we really send this with single photons. And this has happened, but with polarization between a place in the west of South Africa, South Africa, right? West of South Africa, there in Stellenbosch, you know it, and Beijing, that's in China. That was a record, was 12,000 kilometers, right? Where they transfer data, but using polarization. But if you use this OEM values, you could per photon, you have a broader bandwidth. You not only have 2 signals, you have many signals. All right, and at some point, we looked how does this actually work in practice, because you know, if you want to send something to satellite, it has to traverse the atmosphere, and the atmosphere has turbulence, and turbulence is actually this turbulence your spatial modes. It's not so much disturbing your polarization, but it does disturb your spatial modes. And we simulated that in an experiment where, you know, we have 2 photons that are entangled, and one of them goes to a certain, you know, a certain phase grating, and the other one to another one, and this symbolizes like atmospheric turbulence. Okay, and then you can see, is it still true that you get on the one side L equal to 2 and on the other side L equal to -2 or not? And what you will find is that you can do a quantum key distribution, and you get more than 1 bit per photon. With polarization, you could at most get 1 bit. Here it goes up to 1.4. No, this is actually the mutual correction, another measure. Okay, so it goes up to 1.1, but then it goes down again. Okay, so if you use the higher modes, it doesn't work because they are too sensitive to polarization. So in this scheme, it doesn't work except you come up with some clever error correction. And we found a nice scheme to do error correction. That means we send some classical light also to the turbulence and turbulent atmosphere, and we see what it does, and then we correct all the mistakes. So that can be done. All right. So this is what it does, and this is a slide about how one can simulate the turbulence, but I will not go into it. And this is what it looks like. Look how terrible, depending on the strength of the turbulence, how terrible the mode looks. The initial mode is like this, and then with turbulence, it looks like this. So you have to really do some error correction. And what you see here in terms of the correlations, there's a lot of crosstalk. This is what we call crosstalk. If there is not only the diagonal, but the off diagonals. Okay. All right, and then there is something like you can measure the entanglement in terms of a certain entanglement measure concurrency, and you can see that it goes down like this in turbulence, depending on the strength of the turbulence. So now I want to come to quantum teleportation, and I don't know, I still have 1 minute, it's not too much. Maybe we can get 5 more minutes. Can we? 5, 10. Where's Eric? Is it okay? Are you sure? All right, perfect. Okay, so we know already that this thing here doesn't work, right? I don't want to. This was the classical teleportation, but we also know that that this thing here works, there's now another picture of quantum teleportation. So here, this line here is kind of put here first, and in between, there is now these two entangled particles that are sent to Alice and Bob. Here's Alice, here's Bob, and then we measure. We measure on Alice's side, we give the signal to the other side. The signal is totally independent of what comes in here, and then by forming a transformation that corresponds to the measurement result, we teleport the state of the system over there to a remote system or on the other side. It's called quantum teleportation. And it works. Right. So this thing doesn't. Okay. That's also not bad. Then I just go on. So why quantum teleportation? Well, you see, if I have a teleportation from here to there, then I get perfect entanglement between here and there, because this was the entangled pair, and this was the entangled pair, and I use this entangled pair as a resource for my teleportation. Then I teleport the state of this thing to over here, and then I get something that is entangled on a longer distance. So I can use this to stretch much further, right? And if I have two pairs that are well, here's even 4 pairs. Let's say here's 2 pairs that are weakly entangled. I can make a maximally entangled state out of it by a process called entanglement distillation. So I can get rid of the noise by having 2 pairs. So I send the 1 photon through the turbulent atmosphere. It's now noisy. It has less entanglement. Another photon through the entanglement thing. And then I make a measurement from the 2 photons that allows me to recover perfectly. Entanglement distillation. This is how we overcome the noise in the channel, as long as the photons are not absorbed. And the main point is that I actually have to wait until I get a photon here. And I get a photon here, and then I do the same. And then I get this long connection. And the waiting is the problem. So we need, and I told you this before, we need a quantum memory. Okay? We are still working on it. No one knows what it works. You know how it works in principle, but technically it is not long enough. The memory doesn't stay on long enough. All right. So here is quantum teleportation using a filter. So if we just not make a measurement, but just wait until we get a certain measurement result, then we don't have to change things on this side. So then this, for a certain measurement outcomes here, I get, maybe for a measurement from 0, 0, I get this thing transported to here. And we want to use this now for teleportation of orbital angular momentum modes. So we go away from the qubit. Qubits were done before. Our task was to do it for qubits. That means D levels. So 1, 2, 3, 4, 5, whatever D is. Okay. And here is some of the calculation. I will put these files onto the thing, but basically, and you can do it in your own time. I really recommend that you try to calculate this. And basically, this is a maximally entangled state. This is the state between Alice and Bob. And then we have Charlie, who sends photons in, and he has this state. And you must see that the basis that Charlie uses is the same basis that Bob uses. And then you make a projection. This is a projection operator. It projects the systems of Charlie and Alice into a certain state, namely into exactly this state. And it does nothing, this identity operator on Bob's system, because I'm not doing locally only something here. And if I write that down, then I get this combination of B, A, and B, of Charlie, Alice, and Bob. And this thing here, again, is a maximally entangled state. And I'm not Surprised because I project onto maximally entangled state. You know, if I have a projector, I always get back the state on which I project. And this was this maximally entangled state. So what happened now is the two photons that were not entangled at all after this filter are maximally entangled. And this photon here is kind of not entangled, but it carries the same weights or the same coefficients as the initial state here. So this state is now on both sides. See? Okay. This is the trick. And it works for any number of them. So now we can do this entanglement swapping. And entanglement swapping is kind of done with a beam splitter where you get a coincidence count here. This works if you have only two entangled systems. And we generalize this for many systems. And I don't want to go into it. You can look through it yourself. It is quite fun to do it. And then we found a better performance than usual. But the experimental setup looked like this. Okay, so this is the entanglement swapping thing. It's like a little bit like with the beam splitter. You get a photon in here, a photon in here, and if you get a signal on both arms here, then you teleport. You teleport a photon that came in here to here, and then you get a maximally entangled state. And these are Andrew Forrest, Jonathan Leach, in which he is an experimentalist from Scotland, St Andrews, and he did this in his lab. And Steph Roux is my colleague at the University of KwaZulu-Natal, who is a super theoretician. I mean, this guy can calculate anything, you know, and he has a specialty. He calculates everything in terms of generating functions. So, for example, if you have these OAM models, then they are Laguerre-Gauss polynomials, a little bit like in the hydrogen atom. And if you want to solve integrals, you just write down a generating function for these things. So a function where if you take the derivative, you get back the Laguerre-Gauss polynomial. And it turns out all these generating functions are Gaussians. And Gaussians is the only thing. And so you can do anything if you know this thing. I highly recommend to look at its generating function. So this is the thing, and this is how it looks in the lab. Jonathan Leach, you can see a lot of optics. And now, if you wanted to do this for d dimensions, then you would need d times the setup here. But one setup is as expensive as the Maserati. So you need d times the cost of a Maserati. Okay, that's too much. You can't do it. It's not efficient, right? So we thought of something else, and I'm very proud to say that we found something else. This was an idea that was before around, but we were the first that implemented it. Okay, and it's the idea that if you use a nonlinear crystal, then I said that in spontaneous parametric down conversion, you get, if you shine in the light from here, you know, you get two beams out. So this blue light, each photon in the blue light becomes two photons of half the energy. And that is in red, okay? And what is more is that this process also works the other way around. I can also shine in two red photons, get out a blue photon. And the spatial mode here, that's important. The electric field here is the product of the incandescence. This is fantastic because you can do calculations. In fact, and we have never tried this, but if someone is keen, you can use it. If you use it from the blue to the red, you can factor this. It's actually giving you an entangled state of all factors that you can think of, and it's a factor in each one. So you get super much information. No one ever tried. Try to do not Shor's algorithm, but a factorization algorithm using light. we thought, I mean, we didn't do this kind of thing because we didn't know. But for a long time, we searched and for possibilities to do quantum computing with classical algebra. And we found it's difficult, not because we cannot do it efficiently. We can do measurements, the transformations, I believe we can do them all efficiently, but we cannot make electricity. Why? Because if you want to have smaller and smaller structures to store more and more information, you need smaller and smaller wavelengths. It needs higher energy. And that's the point. So we can't do it because even if you have L equal to 22,000, which is the maximum that you can do with an object, because the beams get bigger and bigger. 22,000 a level system is only how many qubits? 2 up to the what degree? No less. Yeah, something like this. So if you get 40 qubits for enormous effort, you cannot do quantum. Except you use non-linearities. That's a difference. And then this doesn't work. So if you want to think about this, do it and become my shore. Okay. So here is the teleportation scheme, and I think after this I stop. The teleportation scheme that we developed using these nonlinear crystals. We developed one where we used the nonlinear crystal to produce these entangled photons in the spatial modes, okay? And another one where we use it to project onto the entangled state, all right? So you saw in the beginning there was this entangled state that Alice involved, pair, and there was this filter which projects exactly on that state. And this is done here, you know. This is like a pump that produces the 2 entangled photons, and this is the 2 entangled photons that produce what we call an anti-pump. Okay, and if we project this thing onto the same state as this pump in the initial was, then you will see that the light here has the same state as there. Somehow makes sense, even if you don't really do the calculations. It is so symmetric, it must be true. And let me show you why. So here is this SPDC, the first SPDC, and here's the second SPDC. We call it anti-SPDC because it's up conversion, it's down conversion. And now let's look here at L equal to 0. So we project here on the same thing as what comes in here, it's a Gaussian beam, all right? And now we put in the L equal to -1. Now, in order to get in an L equal to 0 from an L equal to -1, what do I have to put in here? Well, it is you know, because the phase is in the exponential. You know, it is the e up to the IL phi or L theta, where theta is azimuthal, phi is azimuthal angle. So this thing goes in here, and this thing goes in here, and here's the product of the two. So here's e up to the IL phi, and here's e up to the IL prime phi. And what you get here is e up to the IL plus L prime phi, right? Because exponential and you have the sum in the exponent. So that means what we are looking for here to get L equal to 0 must be something that together with this adds to 0. So what is this number that adds to 0 if you add it to -1? 1, sure, right? So let's try this. So here we have L equal to 1. Oh, it's not coming. Ugh, Jesus. No, we are, maybe it's coming. Yeah, it's coming. So here's L equal to 1, right? So this is right. But if you want to get this right, because these two are the factors, they must also sum to this thing. Then this is clear, must also be L equal to -1. So in other words, if I put in here L equal to -1, I get L equal to -1 out. And that the same is true for any other L number. And since they form a basis, it's all, and this is a linear process in the states, it's also true for all linear combinations, for all superpositions. So I can send any superposition of OEM modes in and teleport them to the other side. And what are they? The superpositions, if they are bases for the wavefronts, it's basically holograms. It's basically I can any optical image I can teleport to a remote place without sending the information directly, because there is no line where information directly. Here was someone who was the one who asked me the question, does it travel backwards to the source? That was the ancient question. That's a really important question. And you know, Zeilinger said, I don't want to mystify the thing, but Zeilinger, one of the Nobel Prize laureates, said, you know, quantum mechanics doesn't really know about space and time. It's playing in a different field, you know? Because we have these correlations that are not like spooky action at the distance. So the thing is, the information travels from here to there, even though there's no connection. It's purely by these correlations that it does with, right? And now you can make an image here disappear and appear in Durham, you know, or somewhere else in Akron. That is just, you know, and maybe we can even do it for massive particles. Okay, so this is what I wanted to tell you, and here are some statistics, but that's not so interesting. By the way, this line here is the classical limit. That means this is what we would have found out if I had at the time to calculate with you the fidelity for classical theory. And in higher dimensions, you know, it goes down. No, it goes to 1 over d plus 1 or something, 2 over d plus 1. So the higher the dimension is, the less fidelity you get in your classical picture. But for images, you need a high fidelity, you need a high dimension. And this thing here doesn't look too good, but it's experimental, you know, and we can still improve it. Okay, so this is what I wanted to tell you, and I thank you for your attention.
Okay. Vielen Dank für die Zeit. Das ist nicht schlecht. Das dauert etwas länger. Es ist halt so, weil keiner Snipe. Aber das ist auch normal. Okay, wie ist das?
Yeah, we have 5 minutes break before I was saying.
Let me say one more thing. If you are interested in working with these things, drop me an email.
Going to the hotel.
Muskeln, ich habe ja das Lied.
Sorry.
War natürlich geworden sein.
Dann, see you later.
Dann see you later.
Ich weiß nicht genau, Lunch hier irgendwie haben.
Dann sehen wir uns nach.
Achso, ich weiß. Es sind nachmittags, es kann ja nicht, das waren gemeint alle online.
Ich weiß gar nicht, was
Also laut dem Plan Irgendwie vor ein paar Tagen bist du sie online.
Gut, das ist nicht so mein Ding. Halt.
Wir werden sehen. Wenn wir jetzt auch schon Kaffee ja, ja, sagt Welt, Bescheid. Das hier. Oh no, it's not working. Oh, it's not. Oh, now it's working. Okay, thanks a lot. Okay, good.
Nana. Program na medicine science room.
Sorry?
Yeah. It's 928 52
2,
77 28
8.
38. Yes. Passport 94 90 20.
Good.
Oh, yeah. Okay. That's pretty cool. Oh, yeah. Good. Good, good. Thank you a lot. Yeah, we start with a little bit of theory, and then the second half we get into lessons. Thank you. Cool. Good, good. Microphone is working.
Yeah, microphone is working. Hello. 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 Hello.
So, hello everyone. Then, hi everyone. We'll slowly start with a second lecture and tutorial for the QML, quantum machine learning. So my idea is to condense a little bit what I wanted to do in the second lecture to the first hour and have the second hour for tutorial. And the aim of the tutorial is to get some first insight into, to go through a notebook, Python notebook. Thanks a lot. From Penny Lane, which is about quantum kernels, to go through it and to make a few adjustments and so on. So this is Python programming. Can you tell me again a little bit who has background in coding and programming stuff with Python? You okay? Okay. What sort of tools are you using? Do you use VS Code? Huh? Yeah, something else than VS Code? Colab? Okay. Huh? Jupyter? Okay, Jupyter is like the notebook, which can also run in VS Code. So who is familiar with pip install or condas install? Okay, that's very good. So there are three packages we need for this notebook, right? One package is PennyLane, one is Matplotlib, and one is scikit-learn. Yeah, the two lower are very common, so maybe you already have them. So if you people who know how to do this can already start downloading the stuff, because otherwise in an hour, like 50 people will try to download stuff at once, and this will maybe overload the Wi-Fi. Okay, so and maybe it's people you already have matplotlib and scikit-learn or whatever, right? But if you can already start installing or downloading these packages for people who know what to do, right? Go ahead, and I will later go around and the others. Okay. So then, yeah, we're going to talk today about quantum kernels, a little bit in general about kernels and feature maps and how they are used in classical machine learning. So kernel is a word that is used in many different contexts. So there's also something like hardware kernels or CPU kernels or CUDA cube kernels, GPU kernels, and so on. So it's a bit hard to discriminate. So there's a mathematical definition of a kernel, which is basically a matrix, a quadratic matrix with certain positivity properties. And there is something which is called a feature map. Feature map is a map which, actually I take the pointer, use it. Okay. A feature map is a map which takes an X, potentially low dimensional, and maps it into a higher dimensional space. So phi of X is living in a higher dimensional space. And then in this higher dimensional space, which is a Hilbert space, I'm taking a scalar product, an inner product. Who has heard of these terms, inner product, already before? Okay. Has someone heard of a Hilbert space? Yeah, okay. So, and the thing is, because if you take two different x's, right, basically assume that you have a finite number of x's, x1, x2, x3, x4, x5, right? And the first x goes through x1, x2 in the as a column, sorry, row index. The second x prime goes the same data, x1, x2, x3, x4, x5 in the columns, right? So for each combination of x and x prime, let's say this one, this one, this one, this one, you get one entry in a matrix. Okay, this is this matrix K here. So I told you last time we're considering a data set, right? X1 to xn, n data points. And these are basically indexing rows and columns of a big matrix, which is called the kernel, and the entries on its position, right? For example, I look at this position, let's say this is the third row and the fifth column, right? So I take the third x here, and the fifth x for the x prime, compute the entry by this inner product. And then this specific matrix, which comes out as a positive matrix, and therefore this thing is called kernel, right? But this is just a name which is coming from this mathematical property. For us, we just use this name. It's called a kernel. K is called a kernel. It's a matrix, and we compute the entries by these inner products. But of course, the question is why are we actually interested in doing this? This comes from a very old machine learning model, which is called support vector machine. So this is one of the first machine learning models which was developed, and something which is called the kernel trick. And support vector machines were initially developed to do linear classification. So assume you have a data set like the one here below, right? So you have here, I don't know how many points are these, 50 points maybe, right? X1, X2, X3, X4, X5, X7, and so on, right? You give all of them a number. In this case, each of these x's has two coordinates, so it's a two-dimensional vector. And now let's assume that half of them or some of them are green, some of them are blue, and actually they are linearly separable. So they happen to be just all of the greens being on the left side and all of the blues being on the upper right side. And then it's possible to find a linear decision boundary between these two sets, right? And based on this linear decision boundary, I can now classify new points. So you give me a new point, it will fall here, right? And because it's on this side of the linear decision boundary, I say this is a green point. I give a prediction for the color of the point. And this is, in this case, a very good prediction because the data set is so easy. Okay, so this is the idea of linear decision boundaries and linear classification. Questions so far? Clear? Easy? Too slow? Too fast? Yeah.
But you can study the characterized quantum set for training a quantum model. That's releasing started a classical data set. So house one, we use a classical data set to train a model. Then after training the model, we would like to test that model. You can take a quantum data set. Test the quantum model perform the
So the question was, let me repeat it, if I have a quantum model, I train it on a classical data set, and then I apply this trained model to a quantum data set. If it's a reasonable thing to do for quantum patterns. So in general, I would say no, but this is actually not about quantum and classical. So if you have a data set, you train your model on this data set, and then you apply the same model to a completely different data set. Say you have a model which is trained to discriminate cats and dogs, right? Now you give the model pictures of castles and trees, right? But there was never anything looking like a castle in the training set. And this model would, model of this other data set will not perform very well. And this is the same if you train on cats and dogs, but then you apply the model to, I don't know, tangle of separate states which don't have anything in common with cats and dogs, right? And this will not work very well. So this was also very So I mean, most of real world problems are classical problems, right? So someone in a bank or at a pharma company or whatever will pay you because you solve a real world problem where you say, okay, discriminate between disease patient and non-disease patient. Most people, most problems people are interested in pay money for are classical problems. So the application made of machine learning models, more classical, is, let's say, much more relevant if you can apply it to classical data. Therefore, we were speaking about these different encoding techniques. So remember from the first lecture. But of course, there are also many interesting quantum problems which are based on quantum data. But these are more, let's say, interesting more to academia, at least currently, right? So also pharmaceutical companies have some interest in quantum chemistry, for example, because it's the very foundation of what they are doing. So there, actually, it's also going a little bit to the overlap of industry interest into actual quantum data. But this is something which is just developing and will become more important in the future. Yeah. Okay. Right, but I mean, very good, because this also recapitulated or brought a little bit back to, okay, what we were talking about the last time. And what we are going to do here is, again, we are having later pictures of these parameterized quantum circuits and so on, right? So it's basically the same. We just apply parameterized quantum circuits here in this context of kernel and support vector machines for classification. And we start just classically and later do the step towards quantum, okay? Okay, but now, okay, I was speaking about linear decision problems. Now, often problems are not linear, like decision and classification problems are not linearly separable. For example, if you have this data set, right, you can discriminate between blue and green points, but you need a nonlinear decision boundary. If in some way you obtain this with a machine learning model, right, then this model will be again very good in classifying new data points into blue and green because everything which is right of this curvy boundary has a very high likelihood that it's actually blue, right? But and now the idea of the feature map is that if you have such a non-linear classification problem, you map the data into a high-dimensional space where it becomes linear. And I will show you a much more clear example in a second, but this is the abstract idea. So you start, let's say, with a two-dimensional data set, which requires a nonlinear decision boundary. You use a feature map which maps, let's say, into 10-dimensional space. I cannot make a picture of 10-dimensional space, so I do like, okay, this would be 10-dimensional space. Okay, it's just a picture representation. So I take this feature map into a high-dimensional space in which I hope that the problem becomes linearly separable, and then I use support vector machine in this high-dimensional space to get the decision boundary. And then if you give me a new point, right, you give me a new point which is here, then I go through the feature map, maybe it lands here, and then here I do the classification. Okay, still it's on this side, I give it a green label, right, and therefore I have a prediction on the new point. Does this make sense, sort of sense to everyone? Yeah, you're looking like it's too easy. No? No comment? So now we talk through a very simple linear classification problem. So let's say you have points on a line, right? You have the green triangles and the blue points, and you now want to learn a decision boundary between blue and green. And obviously, you cannot find a single linear decision boundary between green and blue in this one-dimensional picture, because you need this boundary and this boundary, right? Basically, you would need two boundaries, but you're just allowed to put one boundary. So now I tell you the feature map. The feature, okay, here is basically the description of the function which you want to learn. So you want to have something which is predicting 0 on all the points here in the middle, right? Actually, it should be a -1, sorry. So which is the 0 here should be a -1, apologies. So which is -1 in all the points here in the middle and +1 for all the points outside of this interval of -π/2 to +π/2. And the feature map I'm going to give you, so this is the map which maps 1D to 2D. In the first component, we just keep x. In the second component, we put an x squared. And this is how the data looks like in the high-dimensional feature space. So you see, the x component of the points just stays the same. They all have the same component on the x-axis, but on the y-axis, they get x squared, right? And this means that all the green points land above of this orange line, and all the blue points land below of this orange line. And here you see how in the two-dimensional feature space, you actually find a linear decision boundary which separates these two classes. Okay? Does it make sense? Yes. Okay. So now I have a task for you. So I have here written down the classifier, basically, right? So the classifier of the support vector machine always looks like this. You have a parameter vector omega. You have your image of the point x under the feature map. The feature map is given here. And then you have another linear parameter. And I already wrote down the optimal parameters here, right? The optimal parameter is that the first omega is 0, the second omega is 1, and the b is -π²/4. Now I have a question for you. And then you take the signature, right? So the signature is when this expression between the brackets is positive, the outcome is +1. And if this expression is negative, the outcome is -1. Okay, this SGN takes the argument. If the argument is larger than 0, it gives you a +1. If the argument is smaller than 0, it gives you a -1. And now the question is, assume that y is -1. What is the range where x can be? Okay, so I give you 5 minutes to think about it. And then let's see. Is the question clear to everyone, or does? Question again. Is basically written here, right? Assume here you have this function. Assume that this function gives you a -1. What can you infer about the x? Right? Basically, you have to show now that if this is -1, it means that, I mean, this being -1 is equivalent to the expression in the bracket t smaller than 0. So for which x value is this expression here smaller than 0? But I mean, you would like to have a time that's no, it's not this. It's kind of those instructions, but signature. It's by so signature, let's say, let's call it Z, right? The Z is just a arbitrary variable. It is 1 if Z. So that's the definition of the signature function. And yeah, we already heard the answer. And the answer is exactly this. So this function is negative if x, sorry, here must be an x, is if x is in this interval, right? So between here and here, which is obvious from the picture, of course, right? So in the picture, I'm asking exactly, well, I mean, it's just that this function here, the y tilde, exactly describes this decision boundary. Okay. So if you plug in, let's say, something which is a little bit larger than -π/2, right? Then you're putting this into here. So the first component will be a little bit larger than -π/2. The second component will be a little bit smaller than π²/4, right? Or actually will be a little bit larger. And then you're taking just this one, you subtract pi square over 4, right? And you obtain, right. So the square of it will be a little bit smaller than pi square over 4. You subtract this, so you will end up with something negative here. The signature gives you -1. Same holds for the other point. Okay. Now the idea of, okay, this was about feature map. Okay. Now the idea of the kernel is that we actually don't even have to compute or don't even have to know the feature map. And the important step to derive that we don't need the feature map, but we only require the kernel is basically the step from here to here. And this is something you just have to believe me because I cannot show it right now. But okay, this is what we just had before. This is basically just the same but a different notation, right? So many people already of you saw using this bracket for writing a scalar product. And this is just also a scalar product between this vector and this vector. Okay, I just changed the notation here to our well-known, and not so well-known, our often used bracket notation, basically. And then in the literature, you can read that the optimal omega that you place here can be actually written as a linear combination of feature maps evaluated at your data points, right? So here's a sum of all the data points. Alpha i's are parameters which we can learn. And this is the data point evaluated. Now, the only thing which is left over are scalar products in the feature space. So between these phi's evaluated at different point x's. And this is what I write down here in the last line. So basically, this is just the kernel. This was the definition of the kernel. And now you can
Yes.
hello? You hear me? Okay, how much of the stuff you did not hear because the microphone was on? All of it. Okay, I was saying this step is just a different notation. Writing a scalar product with these brackets. From here to here, I use a well-known fact from the literature, which I cannot prove to you right now, and which allows us to replace the omega, which is unknown, of course, by a linear superposition of feature maps evaluated at our data points, xi. So I from 1 to n is going through to the data set. Then I look at all the data points in the high-dimensional feature space, and I add some trainable alphas here. So the alphas are, in the end, the thing that gets optimized by the optimizer. And now you have these brackets here, and the only thing you have to evaluate is these scalar products, and this is exactly the kernel. So this is what we before called the kernel. And the kernel trick now is actually forget about this step here and forget about this line and just go from here to directly here. Oh, sorry, I forgot the alphas here. Okay, here should be little alphas. Go from here to here and just write down an ansatz for k. Right, k. could be just a very simple function which depends on two vectors, which I just define, and then I don't even have to compute this feature map, which is going to a high dimensional space and can be expensive. Okay, that's a rough idea. And I don't tell you the details about the support vector machine, but this is let's say this is a model which is contained in scikit-learn, for example, or other machine learning frameworks. And this you can just use out of the box, insert the kernel, and this will spit you out the basically the model which can do the classification for you. And this is what we're going to do in this tutorial, okay? So there are two things. Okay, now the question about quantum kernels. And the idea is very simple. Basically, that I compute the kernel on the quantum computer. That's all. So the quantum computer here is not used as the machine learning model, let's say, but it's just used as a way to compute the kernel, and the kernel is then inputted into the support vector machine, which is a classical component. And the kernel, the evaluation of the kernel can still be parameterized, right? So you can still have parameters in the quantum circuits which you also optimize. So the optimization loop in the end will be over So the optimization loop in the end will be over the classical parameters and the parameters in the quantum circuit. And okay, what do we do to actually compute an overlap of two states on a quantum computer? This is now something which is going into quantum algorithms, right? And this is called, there are two options for this. There's an algorithm called the swap test and another algorithm called the inversion test, which are ways to compute such an overlap. The swap test is shown here in the upper corner. Basically, you have a unitary which prepares the first state, and well, no, sorry, you have a unitary which encodes the data. And this is, for example, one of these examples we were discussing in our last lecture. Okay, data encoding. But you can also contain parameterized gates, as I said before. And now you prepare both of these states here and here. Then you apply this controlled swap gate. And then you can show that the outcome here is proportional to the overlap. Okay. So I need to have a quick break. But so in 5 minutes I will go on, okay?
Jump, figure which is going on. Working, or is it not?
It's not finding.
Okay, then do add notebook after
It's better thing.
yeah. Yeah, so hi everyone. So I was a little bit ill the last 2 days. So apparently I'm weaker than I was expecting today in the morning. So what we're going to do is I don't show you the derivation of these things. We just go through the tutorial, right? So this is something where you can work and help each other, and I can just walk a little bit around. Help you a little bit. So this is some derivation of the swap and the inversion test. That's a tutorial. So try to find this notebook here. Okay, follow this link. You can download it on the page. And then you need to have a running Python installation with these 3 packages. And then you run through the notebook, check if it's working. And if you're done with this, you let me know. And then we are going to start with one of these tasks, okay? And please help each other. So I'm pretty sure some of you know what to do to install
packages on the notebook. But maybe some of you don't, so please help me out. How many people know what to do right now? Okay, 5, 4, whatever. Yes. Does not have a computer. Ah. So you're typing in penny lane quantum kernels in Google. And this is not the correct one. Okay, you scroll a bit down. It's called training and evaluating quantum kernels. This is the notebook. And then you scroll down a little bit on the right-hand side, not in the main area, but on the right-hand side here. And there's the option to download the notebook. Okay. So that's the name. Here's the download notebook.
this.
Give me 3 minutes. So some of you already made it to the point that they have this notebook running, right? And they can run the notebook. Here I have a couple of tasks for you. So first of all, you have to understand the notebook, right? You go through the notebook and try to understand every step. At some point, there is the kernel alignment defined. Okay, there's a definition of the kernel alignment, which is a quantity, and it's implemented, they compute it for you and all the stuff. So what I would like to ask you is to look at what happens there, right? Around the, first go through the notebook and understand everything. And then if you have done this, you go to the kernel alignment section, and there they have a loop and increase the kernel alignment by taking larger and larger numbers of optimization steps. So what I want you to do is to plot this in Matplotlib, right? To show it, to visualize the increase of kernel alignment as you increase the number of step size. That's the first task. The second task is that somewhere in the very beginning of the notebook, there is the layer defined. The layer is basically the feature map, which I told you before. So this is the quantum part. You can have any other quantum circuit there. Okay, this function is called def layer brackets. So I would like that you can play around with this, define a different layer, right? So maybe take what's in there and just repeat some of the blocks more often, right? Or use other components so that you write your own layer. And then basically with the new layer, do the same as number one, right? And then ideally compare the old layer with your new layer. Okay, if this improves or not improves. So, okay. So you can start with this and then let me know if, while I'm walking around, and let me know if someone has done the two steps. Okay.
How to start. Or create two separate problems. If, Very excited. Yes.
The one we make up in second.
Good afternoon. I hope you are doing a lot of things by yourself. And we're supposed to have a couple of things this afternoon. So I will not be able to do them. Apart from the last one, I think. So what I'm advising now is that you can take your time and then as you are in this now, you'll be studying what you have been taught and then yes. And then Google documents have some assignments, some lecture notes in there. You can take your time to go through it. And so I think the lunch will be ready very shortly. So after lunch, you take your time to do and discuss all the things you have been taught. And then you have another lab, I think somewhere in the evening. From not, yeah, 4, you have another lab session. Yes. So please, I think by now, lunch, if lunch is not in, you just wait a while. Lunch is all you don't have the lunch. After the lunch, you come together and then take your time, go through all the things you have talked so far, all the practice you have been on the computer and all of that. That's more or less like winding up the week. Because in effect, we are ending the week today. You will not learn anything. You will learn the learning by themselves. Yes, and I've placed on your platform 3 things. One of them, the deadline has expired, so that is cancelled. Those of us who will go by person, we are going to go tomorrow in the morning. Exactly by 8 a.m. the batch session. Please come on time so that you leave exactly by 8 a.m. and go. The next thing which the deadline will end in this 12 minutes is the documentary that the meeting happens. She has ended again. Okay, someone is continuing that 12 minutes passed. Well, I have not made a call to get the things that we want. The main reason for the deadline is to budget for some of the things like the option and you need to budget for the numbers. That's why I keep the deadline on the time. So I haven't called them because I have to see to the lecture. So if you have not gone there to choose whether you come or not, for us, we'll do the number that is coming. So you better do it now. And then when I resolve the lecture going to the hospital and the hotel, I'll have to call the people to budget for the numbers that we have. For the vacancy, I assume that was interested because we have more than 54 hours. So that's fine. So if you want to join us for the documentary or the it's go and then answer the group, then we take it from there. Maybe I'll kind of take a very short time to discuss the romance program because this gentleman gave me the question. That all those who intend to slide will not be any question so we'll see to that one. So thank you. Let's continue. You guys?
I also did the city for the starts with me.
Oh my God, just about where you did see. When I'm saying about saying this, I'm also moving.
Hello guys, sorry for the late switch. Some people have to do that.
Yes, so I like to share thank you picture of it. Hi guys.
Welcome to my YouTube channel.
People are you not good? Oh, I'm not even good. Do me something. But
I don't know. You've been very good. You've been very good.
um, yeah. What You cannot say anything. That's no. Or you want it's Hajra.
Oh. Great. That's stylish.
Okay.
Yeah. Oh, yeah, I said. What do you like? Actually, I will cook. Yeah, that's it. I don't have any cook the cup. Oh, almost as ever. Yeah. That's all. I. Yeah, food there next year. Zoom enter the function. Is it? If we zoom enter the function, I can't. That one, don't think that we get rid of stuff. too complex. Yeah, and you can use this like normal. Yes. Sorry. Mama. Father. But you know that I can go and serve and then I do. And that was this moment now we don't know what it's about. And what of our sisters and mothers who even with fasted, they sell food outside. Oh yeah, fasted on Saturday. On one. Therefore, who are fasting, people from start that application also. Changing the you know what is the address to have in front of the project.
Yeah. If I don't want to refer a fainting now. I'm on this.
He said this.
Ah.
Last one. So I know that was.
See how from that, you know.
Wow.
God bless.
You talk about
Okay. So good afternoon. I guess we have about 1 hour to start the next lab. Then we are done with lectures. Or we are done with teaching. For lecture, you have the lecture which we will continue to study. We are done with teaching. Hi. So, like I said, I think someone asked some question. I just have to try. The form has basically some specific but that I don't mean that that is the only university that we are expected to take for students to apply. So we have the added there. So if the university is not captured in any of the options, but you click on the other, then also you can type in the university. The other thing has to do with the qualification. The qualification profile is very wide in the sense that we're looking at almost all engineering, almost all the sciences in the context of those who do physics, mathematics, chemistry, not science and all of that, because this science is not that into not that into maths and math. So we look at the quote unquote the physical sciences. The physical sciences. So I think those were the two questions that we gave me, right? Yes. And so for us, we're not looking at just the quantum science and technology. I think the flyer says it's all. We have the materials modeling, and when I speak of materials modeling, and what my former provider was doing, the practical simulation of quantum models, they are all materials modeling, or the continuum actual, they are all materials modeling. Then when you come to the quantum science, then you look at the algorithms and things that they are showing you. Then for you, for the other one, I don't think any of you is that area, so it's fine. I'll get it. But the other two other options, videos with smart renewable energy, and that of the hydrogen activity. So yes, this is what we do. This is what we are doing here. I think I've answered all this question. I decided to kind of answer to everyone. Everyone is fine. But if anybody has any other question, ask me now. Because I want to get some money for our non-Ghanaians. Yeah. I mean, your question about I want to get for you today so that for tomorrow you are going to know. So I want to get your question double money for you. So that I can that's okay. Or if you are looking at we ask the question. Okay. Yes. Well, no. In fact, we were supposed to have followed that up. As of last year, non-Ghanaians were not part. We were supposed to have done some internal discussion before. The reason is just people. If in the industry or in Ghana, foreign students have a different amount of fee. And since the program structured that you will give me some funding, and out of the funding, you pay your fees. It's being calculated with the normal fees. So we have to get the vice chancellor to weigh the other side of the foreign fees, and that's why the foreigners we did not add them last year, but since we were doing too many things we forget. So maybe I'll follow up on that and then we'll see if the foreigners are to our, we'll have to make another plan. I'll have to follow up with the vice chancellor, way back in the time. So you, wait for us, we'll get there. Is any other question? Okay, then I guess I can run and go and get the money for our foreigners before tomorrow. They will not be able to get their money with the local process. All right, thank you. But I think Leonardo is coming, the bus is gone for him, so. Leonardo is here. Ah, the bus, okay. For the bus, the media team will come and take pictures of you and the facilitators and also do some bit of interview and all of that. So yes, so they said the media team will then after that they will start. They said we'll come around 3:10 thereabouts. Let's. I think they should be there. They should be on their way. Okay, so see you. Let me go and sort this. Non-Ghanaian.
Short question. Short question. We thought that maybe we take a photo of everybody or so. And for Simon said, so maybe the idea would be that we go down to the courtyard now with the lecturers. I mean, Eric is still in the hospital, right? So he cannot make it. So at least, then we might take another one tomorrow if he's fit again, right? But that's maybe we take now photo. Pardon? Okay. So, so we could take a photo now so that everybody is on the photo except Eric. I mean, he was still in the hospital, right? So he doesn't make it now, but let's say all the other speakers are here. And we have to find, somebody has to find Henry. I mean, Henry was, right? And then maybe we just go down now. And then after the photo, Leonardo would start teaching. Okay, is this fine? Yes. Okay, so then,
They finish
The food.
yeah,
No, they'll come back. They're going for pictures and they'll come back.
and teach again.
Yeah, one last lap.
So wait a minute, if you have any flyer or something, then you just disable the video for now.
Okay, a short announcement for the volunteers. Maybe take the banners. We can take pictures with them. These ones.
Yeah, 928527728 56772838 then 9490 928 9490 0.
So welcome back. Up to the best, start lecturing with 5. We have a lot of time to learn. So change your mindset and come back to work. Harry told us, yeah, you can lecture 2 hours. But you don't lecture 3 hours. I think, I mean, for you. Much. Also, so, but we come along with the other one. I will also keep the last hour much lighter, with something different, the lecture, something that you can, I mean, yeah. Okay, so now, me and most of all Divya, that will be the master of the lecture, I think today. Divya has prepared a lot of, I mean, many notebook, Jupyter notebooks in Python that you can actually use and play. They are in the, but it is out. Wait, so the aim of the lecture is to use the composer. So I think if you don't use the composer, if you are not able to master the composer, you're not able to master Python. So that to understand how the flow is going and how to drive. So, but if you are confident that you can jump on Python, please do it. Really one of you already have experience. And all the material is already online on Edit? No, it's not already. All the material.
Do they have access to the Google Drive? No.
You have access to the Google Drive, so you can check.
Okay,
Yes, but there is material, but I don't know if the Google Drive will just a collector to send them in another drive or.
I'm not sure.
Yeah, is there anyone? Yeah, so the Google Drive that shared with the already did the teleportation 2 days ago on the composer. How many? How many were able to teleport? Oh, good. Okay. Almost out. Okay. Okay, so today we will do a bit more real algorithm. So the ones that are particularly smart with the notebook and just jump on the notebooks. Okay. The ones that are the ones to learn more and think more really on how to concentrate, for instance, an oracle. We often talk about the oracle. Okay. So then how you realize the secret of the oracle. So what we do today is Deutsche algorithm and Groves algorithm. And we will do it step by step. So first design a constant oracle for one qubit circuit and see if it's working. Okay. What is a constant oracle? It's an oracle which is constant when the state is has an equal number of 0 and 1. Okay. The oracle applies to a uniform state if an equal number of 0 and 1. Sorry, no, the constant is just constant.
Yeah, constant.
Consider the balance. So we want to try two different oracles because we don't know if Bob is using a constant balance. So let's try for just a single qubit to understand how to build the oracle. Let's work on a single qubit. Actually, these two you can do now without anything. So how you would design a constant oracle for one qubit circuit? So I have a qubit. Whatever the qubit is composed, the oracle will give the same answer. So think about that. Which gate you can use?
So we want to design oracle for just one qubit. So we have just one variable in the function. So fx equal to, you have to, what should the structure of the function fx be? So that whatever the input is, the output is the same. So what can be the structure? Yeah, correct. Yeah. So identity, so no gates on the oracle. So oracle will have nothing basically. So for this, but we still have to create a superposition first. So there will be a Hadamard followed by, so for Deutsch to make the function, the classical Boolean function to be a unitary oracle, we always need ancilla qubit. So we have to add one qubit here. So this is the ancilla qubit, and it has to be initialized to 1. So we put X gate here. No, it's better if I show in the composite. No, sir. So this is the general structure of the Deutsche. We always have to have an ancilla. We have to initialize the ancilla to 1. Then we create a Hadamard. We send it from a computational basis to Hadamard basis by creating a superposition on both qubits. Then we have the oracle for the constant oracle of 1 qubit. As he said, it's just identity, so no gates. So we directly move on to again measuring the input qubit. So we bring it back from the Hadamard to the computational basis and we measure it. So let's go down. I want to show this state variables. But maybe we can show the state variables. This one is the general structure. Yeah. So this is the general structure of the Deutsche algorithm. If you remember, it was a Guidoni had brought it. So we first, oh sorry, hello. So So this is the input qubit. We are doing it for n equal to 1. That's why we have to count integers. We have to apply equal superposition on the input qubit. The ancilla has to be initialized to 1. We apply Hadamard on it there. Then we have the oracle. The oracle is basically the unitary equivalent of the Boolean function that we want to evaluate. And after the oracle is applied, again on the input qubit, the Hadamard is applied on all the input qubits, and then we measure them. So what happens is if the function that we are trying to measure, if it's a constant oracle, that means whatever the input is, that is if it is 0 or 1, the answer always will be either both 0 or both 1. That's a constant oracle. If it's a constant oracle, after measuring, we'll only get one state, that is a 0 state. And if it's a balanced oracle, that is whatever the input, the output is balanced. So it is either 0, 1 or 1, 0. Then after measuring, we'll get the state as 1. So let's check if it's happening on the IBM Composer. So we have one qubit. We apply a Hadamard on it. We initialize the ancilla on to 1. Hadamard on the ancilla. Then since it's we want to design a constant oracle. So there are no gates in the oracle. It's just identity. And we again put a Hadamard on the input qubit and measure it. So let's see what the measurement is. Okay, as you see, the probability of getting 0 is 100%. Here. That's what is expected because it's a constant oracle. So now let's try to see what happens when you have a balanced oracle. So to do a balanced oracle, what has to be the case? That if we have the input as 0 or 1, the output should be 0 and 1 equally distributed. So the simplest way to do that is just a CNOT gate. We remove this one, where the control will be on the ancilla. So Q1, the target will be on our input qubit. So this will be here. So Oracle is just a CNOT with the control on the ancilla and target on the input qubit. So if you just try to see what the output is for this is, say Q0 is 0, then after applying Hadamard, it would be 0 plus 1 by root 2. With the CNOT, it would be and this one is also 0 plus 1 by 0 minus 1 by root 2. So maybe on the board you can try to see what's happening. Sorry, I did it. This will be control will be the input and sorry. Okay. Yeah. This is better to see. So if we reduce the number of classical registers at one, it would be easier to visualize. So the outputs are either 0 or 1. So we see, so this is a balanced oracle. That means when the input is 0, in our input qubit, the output here will be 1. And when it is 1, then it will be 0. So it's a balanced output. That's why after measuring, we're getting 100% probability of 1. If you just remove this C naught, it will become a constant oracle, and you see it changes to 0. It is the simplest example, simplest function for a 1 qubit oracle in Deutsche. Just yeah. So let's try and yeah, 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 I think that's easier to understand.
Okay.
Okay, now let's see. So what we expect from this is for the balanced oracle. Okay, got it. I was looking for the whole screen. Okay, so let's try or the one with the least pending jobs. as you remember last day also the Hadamard was like the combination of RZ root X and RZ. And if you try to look at the unitary matrices corresponding to these three gates, you will see that when we take a direct product, a Hadamard, we can get a Hadamard gate, the Hadamard unitary matrix. Okay, so the expected result is we should only have one peak at 1 in the state 1. But actually we should, with the hardware, we will have some noise and let's see. Okay, it's done. Okay, so we with 1024 shots, we have like 86% of the state 1 and about 14% of state 0. If we increase the number of shots, this should improve. Let's just check. Let's increase the number of shots to say 8092. So with 8092, it's like maybe percentage is now yeah, it has improved very slightly. But still the ratio is almost the same. So this is not a very good machine actually. This one. Okay, so okay, so we did the first step. That is, we designed a constant oracle and a balanced oracle for one qubit, measured it. So for the first one, you will always get 0, and the second one you will always get 1 or 2. So the same thing, now we can extend the qubit number of qubits to 2. So now it's a 2 variable function for which we have to design a constant and a balance function. So maybe this one can be an exercise for you, and you just look up and try to find a function where so it's like so we have two function variable, and so if so we have four possible inputs, and for two of them the output will be say 0, 0, and two of them 1. So this is the constant function. So we have to define oracle that does this job. So half of the time it will be 0, half of the time it will be 1. So think of some function which connects these two variables, which can give this result. So is there some logic gate that comes to your mind when you see this kind of truth table? Where the inputs are, say, it can be balanced somehow. So maybe we can kind of think this over and we can give this as an assignment. It's very easy. I mean, if you think of the logic gates that you know, that acts on 2 bits and gives one number, just think of some gate which half of the time gives one result and half of the time other result. Maybe I can give you one hint that if you remember the truth table of the XOR gate, or if you use XOR, then we get 0 when both of them are equal, both the bits are equal, and one other word. So this is a balanced result. So just you can try to think of what the quantum circuit equivalent to an XOR gate will be. You know, how the circuit, how many CMOS are also XOR is not directly equivalent to one CMOS. Just try to think. Okay, so this you can try on your own maybe that what can be the circuit quantum gate equivalent of a XOR gate. Let's move on to the Grover's search algorithm. So if you remember how the Grover's algorithm looks, right? This was the general structure of the Grover's algorithm. So the purpose of Grover's is we have a data set or we have states. We have to we want to locate one state among all of them, and then we want to amplify the probability of that state. So what the Grover's algorithm looks like, we have our input qubits, we superpose it equally, then we apply oracle which finds the state that we want. So it marks the state that we want. Then we have a diffusion operator which amplifies the probability of that marked state and reduces the probability of the rest. And finally, when we measure it, we just get our marked state, and we. So this is usually an iterative procedure. So we have to do it multiple times. Then we have to run both the marking and the diffusion multiple times to get, a large probability of the marked state. So let me just give an example of Grover's algorithm for 2 qubits. Okay. So first we need 2 qubits. So for 2 qubits, the possible number of states are 4. So 0, 0, 0, 1, 1, 0, and 1, 1. Say we want to the thing that I will show in this example is, so we have 2 qubits. Among the 4 states, we want to mark the state 1, 1. So what could be the oracle that can mark the 1, 1 state? Can anyone have a guess? Like, so among the 4 states, 0, 0, 0, 1, 1, 0, 1, 1, what is a gate that can only act on the state 1, 1, but will not act on the rest of the 3 states? For a 2 qubit case, we have 4 states, right? 0, 0, 0, 1, 1, 0, and 1, 1. We want to mark only the state 1, 1. So we have to apply some gate which only affects the state 1, 1, but not the rest of the 3 possible states. So can you think of such a gate that? No, in quantum gates, yeah. Just first think about the simple gates, the rotation gates or the Pauli gates. What can it when it acts on a 2 qubit state, what happens? Say x is acting on 0, 0, 0, 1, 1, 0, 1, 1. What's the z? Okay, why? So what will it do? What will the z gate do on the 1, 1 state? So you can't have just a z gate. You have to have a control z gate, right? Because then the control will be on the first qubit, and the z will act on the second qubit. Then only it can mark the 1, 1 state, right? Only a single qubit z gate can't mark. So that is right. I mean, you will need a control z gate, because the control z gate, a z gate only acts on. So, as you know, the action of z on 0, it keeps it unchanged, but 1, it flips its state to, it introduces a minus sign to the 1 state. So if you have a control z, we're acting the control z on 0, 0, 0, 1. So since the control is on the first qubit, these 2 states will not be affected. This one the first qubit is 1, but when Z acts on 0, this will also be not affected. So this stays 0, 0, this stays 1, 1, this stays 1, 0, but for the last one, it flips it and it becomes minus 1, 1. So control Z can introduce a phase only to the 1, 1 state and the rest of them are unchanged. So our oracle for 2 qubits to mark the state 1, 1 will be a control Z phase. So let's a control Z is just like
not the solution. Just
okay, okay. They can try on their own.
5 minutes.
Oh, okay.
I'll get back 5 minutes.
So try to construct the control Z using H and C naught. Maybe.
So we never see control Z. We also only see control naught. Okay. So what is control Z? Is a gate that should do like that. So it should change the sign of the second qubit only if the first is 1. Could you please write the matrix for this gate as exercise in the next 5 minutes or 2 minutes? So the matrix. So every two qubit gates,
8 by 8. Sorry, 4 by 4.
every 2 qubit gate acts on 2 qubit is a 4 by 4 matrix. We have seen the CNO, right? The one that should be control Z and verify to satisfy these properties. Okay. Just an exercise to you to connect to what we have done before. So it should be a matrix similar to control naught, but should be at Z somewhere. And if you have an idea, write the matrix and see if it acts as it should in order to satisfy the criteria of the oracle. Okay. Is it clear? Okay, just a few minutes to do that.
Just the 4 by 4 matrix. Try to write what it is. What the control Z.
Maybe I can just repeat. Okay, so this is what we want. What we want? We want to mark the 1-1 state. What do you mean mark in terms of growth? Raised to -1. Okay, so this gate is doing like that. Applying, I don't know if applied to 0, 0 state, it's giving 0, 0. If this is giving this. Okay, so it's not doing anything except on the 1-1 state. The 1-1 state we want to change time. Okay. This gate is called a control Z, but besides that, can you write the gate that is able to do like that? So can you write a matrix, a 4 by 4 matrix? Remember, you have like 0, 0 here, 0, 1 here, 1, 0 here, 1, 1. Okay, so every unitary is represented by a matrix that depends on the number of qubits. So you will have a matrix. You have, for instance, a matrix with a control naught, so the C naught. Yeah, I told you that it's the control Z now, so you can guess how it's the matrix, okay? But write the matrix and verify that it's acting like that. Okay? Let's do it.
And also try to find a way of how to implement it using the universal gate set like Hadamard and CNOTs.
Yes.
What is the equivalent of the control set with just using Hadamard and CNOTs?
Yeah, this is true because one, you see there are several levels. One is the matrix level, the other is this symbol here, you don't find in the composer.
No.
That's a problem.
Yeah, it's not on the file. It was off. Oh,
Switch it off. Ah, sorry.
oh, now it's okay.
Okay. Sorry.
What try to it the matrix form of Seeger, and then you run the Seeger. You can randomly try to do it. Yeah, so everybody. Now, somehow got it, but
But then.
but now how to decompose it to expense.
Actually,
So say, you know your basic gets, right, agency, right? So shall we start with the Grovers?
I think we can go for that and just see.
Yeah.
Okay, I think that everyone was playing finding the charismatic. Now, how to write this charismatic and only on using the game we have. Problem. Okay, because we can, so the charismatic is sorry. So how you build the charismatic? Well, one way to think is that first you have to act as an identity on the first equation. So first part of the matrix should be an identity. And then you can play with the others and understand that this is actually like that. Why this matrix is called as the controller not? Because the controller is this and this is no. Okay. Sorry, the controller is there. This is that and this is the controller. Okay. The controller is not only this, it's everything. So all the other rest. So if I say you control X, you know what I mean. And you are already because it is control not. If I say control Y, no, here's the Y. Okay. So now how you can write this matrix using only the gate that we have the composer. I can help you and say that the gate that you have to use just the C naught and otherwise, but you can arrange in a particular way. Okay. So how to do it? Oh, I don't know yet. Maybe we can at a certain point also pass to the next go to the next step. Yeah. But you have any idea how to do it? You can try to see, I mean, basically, the problem, what is the problem? The problem is that you have to make a set. Okay, because in the control not, here you have a not. So you have something completely different. You have a matrix which is the other way around. 0, 1, 1, 0. Okay. So this is the only 2-qubit case that you can use, and then you have this matrix here. But then you have to find a way to, in some way, to transport this matrix using another mass into Z. Can you do it some way?
So the relation between X and Z. How can you go from X to Z?
Yeah, basically. Yeah. But then if you don't write the paper and start multiplying,
Yeah.
it's not something that comes from
Yeah.
Since it's almost.
So try another couple of minutes to multiply some matrix and see if you. And then
I will tell the answer, yeah, directly.
That's 2 minutes.
On WhatsApp.
Yeah, but the good was to understand the process. Okay, I want the oracle, then I have to think about how I would act on the states, and then I would build the matrix, and then you build also the implementation of the matrix. Yes.
No, this is cheating.
The computer is fine.
Okay, so the. So this is a CZ that, yeah, okay, the.
No, but I'm not sure.
Oh, okay. The composer can also have something very good version. But that's different. So, it's not a native case set, so you can create any case you want. Time for the solution.
They are trying to
Ah.
explain another
That's good. No, because Henry is sending messages constantly. Support.
What did you say?
What do we want for support? Fried rice or potato chips?
Ah,
Okay, potato chips are winning.
potato chips.
But how can I?
What do you mean?
just
Only
put
potato chips?
Only.
Only potato chips? Yeah, potato chips. I'm sure it's a question, so I'm not a
Yeah,
I'm playing.
Yeah.
Stuff.
So the explanation for the diffusion is we have to create the mark state.
This is much easier.
Yeah, so we create the mark state in each of the states. So 0, we have to transform it to 1, 1.
Yeah.
So the 1 also to 1, 1. Then we have to again apply the oracle, and this is how it diffuses, right? How to explain the diffusion of it.
I just.
The structure.
Yeah, but I know.
No, I know how to
So I
explain it, but how to explain the implementation. For example, so this is is not right because I did not know that I did this. Then X is X on this is X is one on go to one. Then we do the same thing, but it's reverse okay. And get back to this as well.
So all these.
Yeah.
Yeah.
How do you generally explain the difference? How does it amplify?
It's amplified because what you draw.
Yeah, yeah. This mathematical form.
Matematica nel sì.
Oh, but that is the order.
No, sorry, it's
This one, yeah.
it's the same, but
This
this
one.
one says,
So 200.
yeah, so this is
So we need a hard amount, so we have.
yeah, so we have good position and look at that. So what happens on all these things?
Okay. 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 Okay, so the form of control Z in terms of Hadamard and CNOT is just Hadamard. So you see, after applying this, yeah.
Okay, so what's your thing probably? This is always. So. That's busy. So there should be correct, but
Okay, so as you can see that for applying, so first we create equal superposition by doing two haramas. So there is equal superposition of 0, 0, 0, 1, 1, 0, 1, 1. After applying the equivalent of a control Z, only 1, 1 changes the phase. So it becomes red and the rest are all positive. So this is the oracle has been defined. Now what we have to do in the next step of Glovers is, so now we have to use the diffusion operator to amplitude for the amplitude amplification of the state 1, 1. And the structure of it is, we have to apply Hadamard on both qubits, not gate on both. Then again we have to apply our oracle. So how did we form our oracle? And then we repeat the same thing but in a reverse order. So X, X and Hadamard are 1. Now you can see with this, so we just have one, the state 1, 1 left now. All the others have gone. So we have successful. So what we did, the first Hadamard, CNOT and Hadamard was our oracle. The next gates are all our diffusion or amplitude amplification. And then obviously if we do a measurement now, so the diffusion operator is 2 Hadamards, then we put 2 X gates on both qubits. Then we repeat our oracle, that is H, C0 H, and then we do the same thing in reverse order. So two knots and then Hadamards again. Then we measured it and we see that. Now another thing that he pointed out. Yeah, sure. Yeah, it's all. But I'm trying to like make it look more clear. So
because
everything is side by side.
common entity. So
Okay. Instead of barrier. Yeah, this looks good.
okay, can you explain everything from scratch because they
Yeah, so so first the two Hadamards that we have is create the equal superposition state, that is 0, 0, 0, 1, 1, 0, 1, 1, all equal for the weight. Next, we since we found out that control Z gate has can only flip the face of one and rest of them are all, it stays the same. So this is the equivalent of control Z gate. So Hadamard, C0 and Hadamard on the target qubit.
That's why you put his identity.
And yeah, so the identity is just to make the things clear. So up to this is our whatever, which marks the scale. After that, the next part up to here, this constitutes our diffusion operator. So the target of a diffusion operator is to slowly increase the probability of the state 1, and reduce the probabilities of rest of the states. So as you can see, when we finished on applying our diffusion, we see that only 1 has the probability and the rest of them are almost zero. So basically that, and the other thing is, instead of decomposing our control Z to H, C0 H on the composer, there is also a way to, so instead of using this, we can directly use so you can see that there's a way that you can add a control on any gate. So this is equivalent to a CZ. And so the same thing we can do here. We remove Hadamard, C0 Hadamard. Put a Z gate here. Add control. Okay. So that is our circuit. This is another way to do it on IBM Composer, but usually when you do it on Qiskit or Python, you have to decompose it in terms of H and C0, because those are the native gate sets in IBM usually. Okay, so you can see very clearly that we have only 1 with a minus sign in the final statement, -1 and H.
So one single shot was enough.
Yes, because this is a 2-qubit case, so we need only 1 iteration to amplify it. When we have 3 qubits, then it will need like I think root n iterations is the optimal. So root 3, something like that.
But n is the number of states. So.
N is the number of states or qubit states? Okay.
Yeah. Yeah. 2 bits.
N is the number. Okay. Yeah.
N is the number of qubits.
Number of
No,
qubits.
it's the number of qubits. Yeah.
Yeah, number of qubits. So what you can do is, as an assignment, you know how to set up and run this on hardware. Just see what happens when there is when you run the Grover circuit in presence of noise, and plot the histogram and the probabilities and check how it compares with the ideal one. Okay, so just for today. Another thing that you can try is instead of marking the 1 state, try to think of oracles which can also mark rest of the 3 states 0 0 0 1 1 0. So if I want to give a hint, then try to convert all the other states to 1 1. Then it's very simple. So convert 0 1 first to 1 1, and then just apply CZ, and you can mark it. So that's the easiest way to do. So do you want to tic-tac-toe or okay?
Okay, now
Some magic.
as a last day, we have something more relaxing. So you will have 5 minutes show of something, I mean, everyone thinks that there is something magic in quantum mechanics, no? And so what we did at the University of L'Aquila is we created something which looks like normal cards, but it's actually, these are normal cards, right? So it looks like normal cards, but actually they are quantum cards. Okay. So whatever you are seeing today is now it's just very big. Okay, but it's nice to communicate the strange stuff of quantum computing, and because when you see a microscopic object behaving like a qubit, then say, oh wow, that's cool. So we'll do this, and then I will want to teach you a quantum game by pen and paper that you can play with your people. Okay, so which card is it? Card is not. So the superposition of two primary values. Okay, so it didn't decide yet if it's a queen or a nine. It's just a card, it's a mixture of two. Okay. So how can we collapse this card in one of the two choices? By measurement. Oh, you learned something. By measurement. How can we measure? So we can measure with some quantum. Do you have some quantum measurements object? Your pen is a quantum measurement object. Okay. This will force the card to collapse in one of the two states. Okay, so we can put the card here. The problem is that the microphone, I cannot do things when having the microphone, so I will not remove the microphone.
Yeah, for this one, we can.
Okay, so you have this fantastic object here.
You are coming from.
Yeah, we're coming from Angela. You see nothing is inside, of course. And so you have this card, you want to put this card in here, so there's nothing there. Okay, yeah. Okay, so now the card is there, and then you're still living in the superposition until you touch with your pen this. You wanted this to stay. Let's see if it's true. Right. You see, not in our laboratory here. We take a lot of courses. Of course, it might happen that let's say here we have another one, like a little one to come here. Volunteers. And another one, then you can put here. Of course, now the card is still in the superposition until the magic pen of two weeks. Not touching up of this. No, so just put it here, the side. Okay. The key. Random, want to do something more. We want to have a bad state. What if you have a bad state? Look out. Yes, yes. we have two cards, but these two cards are entangled. You don't see them because you see only when you measure us. You don't see, but we have entangled this card and that card. So they don't like to be like that. And when one is measured, the other also is measured automatically. Okay, yeah. So we can put one card here and the other card there. We can go very far away. Okay, we can go very far away. The one would be measured. The other one, we don't need to. Relax a bit. Also, this is to relax a bit, so you can learn a quantum game to play with your friends. So this is a quantum tic-tac-toe. Did you ever play to quantum tic-tac-toe? Wow. You know tic-tac-toe? Yes. Tic-tac-toe is a very stupid game. Because I mean, if you learn like when you were very small, and then you realize that okay, if you are playing well, you never lose. Okay. In quantum tic-tac-toe, it's a bit more tricky. And how it's working? So you have to choose. You have two options to put your sign. So you can put. So you can take a paper. Please take a paper and do this drawing. Okay, I will explain and then you can play. So your sign is on a superposition of two different places. Okay, so your X can be either here or there. It's still in a superposition. Okay. It's like a bad state. That means that then when I do the measurement and I found X here, it cannot be there, and the other way around. Then the next player can play another symbol like 0, okay? And he played in this way. So you put here and here. You can put as many symbols as you want in one single one single part, because they are not yet measured. Only at the end there should be only one. Okay. And then the red player also play and play in this way. You see, I drew some line to connect everything. That means that I have to be careful that at the end, if I found this X3 here, it cannot be there, it cannot be there, and the other way around. Okay? And then you continue playing, but you stop at a certain point when someone, like the 0 player, is actually closing a loop. So you have a closer loop in your entanglement state. Okay. So when you have a closed loop in the entanglement state, the other player, so the one that didn't close the loop, can choose, can do the measurement. Okay. So that means that X X player is doing the measurement, and he or she can decide if X1 is here or here. Let's suppose that the player decided X1 is here. Okay. So X sign is here. That means that it's not in the center. So the one in the center should be cancelled. Okay. So, but if X1 is there, that means that O2 is not there. And that means that O2 is here, because if it's not there, it's here. Okay. And then you continue like that. So O4 is here because it remains alone. You have to be a bit careful that the number of box occupied should be at the end the number of. I mean, there are some cases when it's not so easy to understand how it's going on. So O4 is there. That means that O4 is not down there. And that means that there is X3, and X3 is indeed not there. Okay, so now these 1, 2, 3, 4 parts are becoming permanently of the owners, are becoming like that. Okay? So, and you win when you have 3 in a row or 3 in diagonal. It's interesting that it might be that you have 2 winners. So it could be that you have 2 of them together at the same time. Okay. In this case, you can remove. I mean, you can say, okay, no one won, or you can say that it won the one with the lowest, with the 3s on the lowest, with the lowest number. Okay, just repeat, and then you can play. So connect to. Until you have to draw maybe with the pen this connection, because as soon as you have a closer loop, the other one will choose and remove we will make the measurement. And so, and then you start from one point and you continue up to all the points until on each square, only one symbol is remaining. Okay? And then when you arrive like that, you then continue playing on the square which are remaining. Okay? So just find your neighbor and play at least one of these now. These are the rules if you want. These are a summary of the rule. If you have any problem in deciding how is the final, you can tell me.
The laptop is about to shut down. The laptop is about to shut down.
Oh, okay.
Yes.